So what you see in this particular drawing is that you have this piece of metal that is 3.5 inches long, 1.4 inches wide, and 0.25 inches thick. We're going to be milling it out of a piece of aluminum that's represented by this shadow box in the isometric view. That box is actually 1/2 inch tall, so plenty of extra material here, but it's 1/2 inch tall, and it's just over 3.5. In fact, it's 3.6 inches long, and it's just over 1.4 inches wide. In fact, it is 1.5 inches wide. You see that the corners have a radius on them of 0.1 inch. There's two rectangular or oval features here, and those are 0.38 inches wide. You can see I gave a dimension from the center line, and that will become obvious why I did that later. You can also see that the end dimensions of each one of those rounded rectangles is given in the dimensions on the side view right here. So it is 1.45 inches from the center line to the far end of each rectangle, and it's 0.67 inches from the center line to the beginning of that rectangle. That means that each of these rectangles is 0.78 inches long. There is a 0.65 inch diameter hole that goes all the way through the piece. However, there is a 1.103 inch, that's actually 28 millimeters, but 1.103 inch diameter pocket that goes down 0.1 inch. So that's our print that we're going to be working off of, and we're going to be referring back to that. Let's take a look at some of the other things I have for you. So you also have a spreadsheet, and this spreadsheet is pretty extensive. There's a lot of data on here, but if you recall, back in the first semester we went through a lot of feeds and speeds data. Well, I went through and I crunched all that feeds and speeds data here for you. Some of this will make it a lot easier when we're programming our CNC mill to make these aluminum parts. So what we have here is some tool numbers. Each tool is assigned a tool number. There is a method to this madness here. What ends up happening is in some of these areas, like for the square end mills, if something ends with a 6, that is 6/16. In other words, that is a 3/8 diameter tool. So a 5 is a 5/16, a 4 is a 4/16, or 1/4. And so those tools just makes it easier to learn what those different tools are. So when you are using tool number 4, you go, oh, yeah, that must be a 1/4 inch diameter or something. And we tend to follow that structure as we go through, although not in all the cases. But we try to make this as organized as possible, because there's a lot of information here. So you have some designation for the tools. These first ones are all square corner end mills. We have these radius end mills. Actually, there's only 2 of them that we have all the data for. Those are the 2 that we actually have in stock. If we look across, it says the number of flutes, in other words, the number of cutting edges. Most of them for the end mills are 3, although you can see a 16th inch one only has room for 2 flutes. Tells you the cutting length, in other words, the length of the flutes. Tells you what the corner radius is, what the angle of the edge of the tool is, and so, of course, the square corner ones don't have a corner radius. The overall length of the tool. If it has any kind of coating on it, sometimes they have special slippery coatings on it. The vendor where we buy it from, their part numbers, so we can order them easily if we break one. RPMs, so the speed that we spin them at in our mill. And some of these we spin at 10,000 RPMs because they're a small diameter tool, and 10,000 RPMs is the maximum that our machine spins. Axial depth of cut. So think about the axis of the tool, or along the length of the tool. This is how deep you can cut with this tool. And for the data that we have included after this, it is for a cut to this particular depth. So if you use a, say, 1/4 inch tool, as it turns out, this 1/4 inch tool can actually cut to a total of 0.75 inches deep. It has a 0.75 inch cut length. But all my data here is for when I was making a 0.6 inch depth of cut. And what I found is that if I was using a 0.6 inch depth of cut and a radial depth of cut, in other words, how far into the side of the piece of aluminum is it cutting with each pass. And so this is 0.0275, so that's a little under a 32nd of an inch. That's pretty small. How much of a bite it is taking every revolution, 6/1000ths of an inch. How much each one of those teeth are biting off themselves. There's 3 teeth, so that's 0.002 or 2/1000ths of an inch. If we were to measure the speed of each one of those teeth as it's spinning around at the perimeter, as it's spinning along the circumference of that bit, it would actually be 655 inches per second, sorry. And then finally, one that is really important to us is this inch per minute feed rate. Now, when we go to make this part, we're going to be referring specifically to this line right here that has to do with the 1/4 inch end mill. So we're going to be talking about that one quite a bit. We'll be referring to these numbers right here. So tool number 4 is going to be very important to us. And also tool number 57. Tool number 57 is a size F drill bit. We have drill bits that are, of course, fractional size, like 3/16 or 1/4 inch or 1/8 of an inch. We also have some very small drill bits that are number sizes. This is a standard numbering system. And you can see they have some very precise sizes, like a number 25 is 0.1495. That's one of the drill bits that you use when you were tapping holes. That's where you have 1024 right there. We're going to be using a size F, and a size F is just barely bigger than a 1/4 of an inch. As it turns out, the size F is the perfect size tap hole for a 5/16 bolt, or a 5/16 tap hole. And so this particular drill bit has a 0.257 inch diameter, 2 flutes. Its cutting length is 2.875. The tip angle is 135 degrees. The total length of the whole tool is 4.18. It actually has a coating of titanium nitride, which is a specially heat dissipating material, and also it helps keep the tool lubricated as it's drilling. We use a speed of 4,600 revolutions per minute, and as we drill a hole, we're going to peck that hole. We're just going to do 0.063, that's about a 1/16 of an inch, deep pecks, or deep little holes, one right after another, as we peck down through the hole. That results in a feed per revolution of 0.03. In other words, each of those cutting tips is removing just 0.0015. That's a 300 inch per second surface speed, inch per minute, inch per minute surface speed. And finally, the feed rate, how quickly we plunge down into the material, is 8.2 inches per minute. Okay, that is 2 of the 3 things I wanted to show you here. The third thing is where you're going to need to go to log into the simulator for being able to do this. We're using the control software for our Tormach mills. That control software is called PathPilot. It's a great interface. They do have an online version called PathPilot Hub. And so PathPilot Hub is what you're going to be creating an account on. This is approved by the school district. So when you go to PathPilot, you're going to need to go to create an account. I've included a link to create an account in the Google Classroom. You can just click on that. You're going to need to put your first name on there, an email address, and put in a password. You don't need to put your last name in there. I don't care if you check, maybe check that you're using it for school. It's good for them to know that. And you don't need any news or updates or anything like that. But make sure that you have a password that you can remember.